Thank you for the introduction. We are in emerging technologies, as you have introduced correctly. We provide resources to engineering institutions on emerging technologies. We were in electric vehicle, hydrogen vehicle, artificial intelligence, Gen AI, etc. Now, the present interest and topic is also quantum. We are in quantum for the past 3 years. We are providing the resources for establishment of lab in quantum technologies. So my presentation today is to give an orientation of how to establish a lab for quantum technologies. And in this, we have taken into account as guidelines what has been provided as curriculum by both National Quantum Mission and AICTE. They don't differ much, and our presentation will be based on that. So can I go ahead with the presentation?
Yeah, please. Yeah, sure.
Yes, I can go ahead with the slideshow.
Yeah, please. Yes.
Okay. Now, this is the topic today. And now quantum technology, bringing it to life in a laboratory. Now, for the establishment of the lab, first of all, we are looking at the resources that are available that can be made affordable to the institutions. And then simultaneously, we'll also have to map the curriculum for the resources and as well as for the faculty to create lab contents with respect to creating experiments, engaging students from basics onwards to experimentation, and leave some space for them to do projects or research. Is it clear, the screen?
Yes, it's clear.
Okay. Now, we are given guidelines by both National Quantum Mission and as well as AICTE that there shall be 4 verticals. The 4 verticals are with respect to the technology involved, different dimensions and domain. One is computation, the other one is communication, third one is sensing, and the fourth one is materials. So I've only left out the quantum in each of, but quantum computation, quantum communication, quantum sensing, and quantum material. Now, all these verticals, we are supposed to cover both the theory as well as the curriculum is concerned, fundamentals, theory, and then the laboratory part of it. So for that, the resources with respect to theory is always available, but if you have an hands-on to touch on these subjects from theory onwards to practice, it will be handful for the faculty and as well as the students to learn. Now the lab, if you divide it, there is one is a curriculum, which gives you information on both the theory and practical part of it. And then the second part is the equipments that can be used to achieve these objectives. The objectives could be for quantum computation, learn computation using either real qubits or simulation, depending upon whether how much you can afford, what you can afford. Then the communication part of the same thing, different communication techniques, photonics, etc. But majorly, we are more interested in the QKD cryptography part, which is now can be implemented directly because of the advances now we have made in this direction, and also availability a part of it. Though there are a lot of research is going on, but industries have come to some extent to implement this communication and cryptography techniques. Then the third one is very interesting and parallelly going on is quantum sensing. That is measurement of certain parameters through quantum sensing objects. It could be anything. And these quantum particles, quantum bits or photons, materials basically will be involved, can make very minute changes in certain measurements like temperature, magnetic fields, etc. They can find out these minute differences, which will be of great use for the researchers and also can be put in practice. The materials part of it is connected to all the three verticals above and more. Quantum materials form part of it. Superconducting materials, photon materials, etc., which can be put into use in any of the four above or three above verticals, and a lot of research is going on. Now, when you come to creating a lab, affordable lab in any institution, university or college, computation and communication and sensing, it's easy to implement because these are all related to both education and practice. But wherein quantum materials is purely on research, it involves a lot of manufacturing process. So it can mostly be covered only by theory. Now, up to this part, we are only covering the top topics, giving you headlines of what we are going to do. Now, as far as the basics are concerned, ACT and NQM has given certain guidelines. So when we initiate the process of creating the lab, we have to give foundations on quantum computing, technologies and applications, and quantum technology foundation separately. For all these things, if you are having a learning system in your institution, we need to cover the basics. So suppose the learning system that you buy or you keep can include these basics also into your equipments, then it is easy. Otherwise, this can also be covered by presentations. There are interactive systems available for the system for the students to learn. Some of them what we provide are both interactive and game inclusive. That is, you can play a game with the system to understand these basics and fundamentals. So the outline is, when you start a course, we are going in for foundation, which are theoretical, as well as you can learn the basics of these fundamentals with respect to quantum, what is a qubit, etc., until what are the gates, what is a gate, what a circuit consists of. All this can be understood. Quantum physics and quantum mechanics have a lot of fundamentals. Now, as far as students are concerned, we are trying to bring in students or who are interested, or we are trying to. Hello, some noise. Pardon, sir? Pardon, ma'am?
I think
some other. Okay, not muted.
yeah,
Okay.
some noise. I think please mute the mics. That.
Yeah.
Also.
Okay. Now the fundamentals of it, whether it is NMR phenomenon or in the basics of spin qubits, which is involved in quantum computation and quantum sensing. If you look at it, communication also, Rabi isolations, etc. These fundamentals we can give in the initial stage for the student to learn. When it comes to quantum technology lab, now what do we provide them? Now, hands-on training systems are always helpful in quantum computing, communication, quantum sensing, and optics. Now, these are systems where we execute or create quantum communication circuits, quantum computing circuits. We can use to do both the practice of computation with respect to certain algorithms, or mere communication, send and receive data, or quantum sensing for that matter, sense some parameters on some example given as a sample. So that is possible, and learn quantum optics, diffraction, interferometry. All these have some meaning as far as the real quantum equipment is concerned. And for all these things, we also are asked to equip some test and measuring instruments like vector network analyzer, spectrum analyzer, and some basics are required. So we need to have RF integrated circuit and FPGA components, and basic understanding of certain circuits like RLC, logic, etc. Now, these can be given as a trainer or component, but ultimately the guideline given is to have a composite kind of a lab where we will be touching all the four verticals and also basics of certain principles in quantum electronics and computation to learn so that we can directly delve into quantum most important or most interesting domain as far as the student or faculty is concerned, whether it's computing, communication, or sensing, we can go directly. But these are the fundamentals we have to go. Why these fundamentals are required, I'll also address later. The first part we'll address will be quantum computation. What quantum computation, how we can create a lab for quantum computation is, our computing system is in your lab. Now, for lab size quantum computers using real qubits, which means you have to have a room temperature environment for lab size. That is only available in NMR-based quantum computers and NV centers in Diamond. If we use that as a quantum computation, only it's available only these two. The next level, if the university or the center goes for gross of investment, then we can go to superconducting quantum computer, which requires millikelvin temperature, which is provided by dilution refrigerator. That's a totally different subject. Now we are more concerned about equipping our lab affordable and that we can run with minimum maintenance. So for that, if you look at quantum computers, NMR based and NV centers. NV centers are at least twice or thrice costlier than NMR based. NMR based, the best one to have. It is real qubits, and you can execute all the quantum gates on qubits. Multiple qubits up to 3 qubits is possible in NMR. And we can do the computation using these universal gates, creating circuits, test the algorithms, all that is possible. Now, the same lab, the quantum computation can also be done using simulation, which is not hands-on. It is left to the creator how they are brought in using GUIs, the working of quantum, how it can bring it to life, similar to what is happening in real qubits. So these are available as freeware and also pay per use. And now these quantum circuits and algorithms, we can also create using open source program like Python and QASM or Qiskit. There are libraries available using which you can create. Ultimately, what we will be doing, whether you use is open source or freeware or real quantum, is to apply these universal gates in a particular sequence and entangle them as well with multiple qubits are there to create a quantum circuit and run it to know multiple measurements over a period of time within the coherence time and have the probability answer. How the probability is giving you the answer, they are all dependent on algorithms. You will know in the due course. You would have by now given a lot of fundamentals on this, so I leave that name, imagining or assuming that you know that. Now, the cross-platform, that is, we can create the quantum programs on the real quantum computers, and also simulations are available in the same quantum computer or in a PC standalone station. It is possible. And also using open source, as we have said above, you can create the circuits and algorithms. Then we can also connect to superconducting on a high-end quantum computer pay-per-use. So all these things, ultimately the idea is to have a quantum computation and have a lab related to the subject, give the fundamentals, learn using the quantum physics and quantum mechanics and key parameters, functional, or I would say fundamental properties of qubits, which is nothing but superposition, entanglement, and also coherence. So this, within this, how we can create circuit, how we can deduce results from any algorithm, and why the algorithm is created. For all this, we also have the basics of linear algebra, etc., which are also covered in subjects. When we give fundamentals, we cover that aspect also, mathematics, which is involved in this. That's also covered here. Further to the same. Now, when we do the computation or simulation, what kind of experiments we can do? Both the basics as well as real experiment. We can find a Larmor frequency, which is important in spin qubits, especially the frequency of the position in magnetic field due to magnetic field, that Abbe oscillation using different RF pulses. Now, these are all parameters, important parameters when we do computation in NMR-based system. Also in quantum sensing, it will be there. Now, also next, we will use a real qubit, or in a simulation use that qubit, perform the spin around different axes, record the qubit states, analyze the relationship between spin phase and the phases of the two-wave functions are available, and then qubit analysis. Observe all this quantum superposition phenomena on a quantum bit. The other important thing about any system when it's applied to you or you designed a quantum computer is a decoherence. The time before the external factor affects the measurement part of it. So for this, we can do the experiment and measure this T1, T2 levels. These are the levels, the time until the decoherence happens. So T1, T2, and rabbi decay time are the parameters involved. This can also be really physically experimented measured. Quantum control is experiment the single qubit rotations, which are, if you look at it, are also can also be named. If you have a specific rotation, they are called quantum gates. And the entanglement, 2 or 3 qubit entanglement in a smaller lab, or multiple if you go to superconducting. Then we have to have the understanding of quantum logic gates and the quantum circuits. Now, quantum circuits is nothing but creating a circuit, sequence of quantum gates, Hadamard or Pauli. You can create all these gates, put it in a sequence, including entanglement where it's required, multiple gates or single qubit gates, do the universal logic operation by implementing these gates. So that is also part of your initial stage of understanding quantum computation. Tomography is measurement part of it, multiple measurement part of it. And this is important. These measurements are important for reconstructing the quantum operation at a later stage. So that is also included. Then we have this quantum computing task, which is doing the computing and do the verification or application of algorithm. And that is also what we do, what we teach, what we can teach to our students. These are all we are talking about with real qubit based quantum computer or also simulation. Now, with the real qubits, there are many advantages. These are all the experiments you can do. Execute algorithm. I'm again limiting this to the lab size quantum computers. Exceeding this will be that is with respect to number of qubits you may require for certain algorithms like Shor algorithms. It's not possible to apply or implement in a 3 qubit. It requires more qubits. So that we'll have the simulation given by either we give in our own computer, and also we give with our freeware. So the freeware will allow you to do multiple qubits usage and implementation of higher range algorithms. So all these experiments exclusively given to you to give to students working on the real qubits. Then we have now gone on to this qubits, experiments, computation, algorithms, etc. But there are some very basic physical level experiments that we can basic to or even advanced. That is, we can understand the implications of certain parameters in our quantum computation. These are all the parameters you can measure. You can apply certain signals and measure these parameters in our quantum computers. So if you look at why this RF is coming on and off, there may be a question. See, the thing is in the communication between qubits and the measurement systems or the control systems are at present using RF cables, RF communication. So it is part and parcel of quantum as of now in both NMR and superconducting quantum computers. Superconducting quantum computers involving qubits from 5 to hundreds, so now thousands of qubits. All these processes where these manufactured qubits are available in a dilution refrigerator, that is, which can go up to minus 273 degrees. The communication is by connecting individual qubits or two qubits, dual qubits, by RF cable to control and measurement racks. So each qubit or multiple qubits, generally 1 or 2 qubits only per system, will be controlled, and pulses are given through RF system. So there will be RF communication. So that is necessary to understand. We have to understand the usage part of it and what affects a RF signal, what are all the components involved in RF. So these are all there. And also the type of pulses we give and also kind of gradient field. These are all other parameters which can affect that also we do. And measurement, different measurement modes are available in quantum that we can understand. Custom measurement can be introduced. The free induction, these are all available in our quantum computers. So you can collect and understand and perform as well as understand. So these are all available. These poly components are very basic and fundamental components that you can understand, measurement of poly. That is, that may change direction into any XYZ poly. Then we go into the next advance of creating a quantum circuit. Now, what is creating a quantum circuit? Select the number of qubits, select the gates, and put it in a sequence, all 3 gates. Wherever entanglement is necessary, you have the entanglement between the qubits. Then at the end of your you have created some gates, 8 to 10 gates, and then at the end of it, you do measurement. That sequence of creation of it, these are all by drag and placement, simple movement in our GUI-based system, a general GUI-based system with any manufacturer. And you can also do the same circuit, create same circuit using the open sources, Python or any other source. But ultimately what they will do, the Python also will do the same thing. You are creating the same thing. Qubit 1, add a mod gate. Qubit 2, add C not gate. Like that, you will write the same program in a Python and execute it. The advantage being you can create a program elsewhere, write a program elsewhere, and then share it. You need not have access to the GUI of the system. So these are all the things we can do. And then we do the parameters, bottom level parameter, raw data we can create and do the experiment results. The experiment results can also be represented in block spheres. Block sphere you would have been introduced. Now I'm sure I'm the third or fourth day of your learning process. So block sphere is available in learning system, and in our case it's available, and density matrix is available as experimental results. Then we go to classical hybrid. Now window based personal or advanced power stations, we are workstation you have, where we can create this classical hybrid programming and experiments. That is basic. What we are trying to say is convert a normal problem, a classical computer problem, into a quantum problem. And for that, there are some optimizers, there are some ready-made algorithms you can understand and implement it. So this is as far as quantum computing is concerned. We have so far covered real quantum computer. Same thing in a simulator. We have the same thing as just now we were explained. So you do the same quantum circuit creation by simulation. If it exceeds 3 qubits, you can go up to 8 to 20 qubits on the computer itself or an external computer. As far as we are concerned, we give like Qiskit, we give one spin kit, which can create the same programming circuit and in a simulation with multiple qubits up to 20, 24. That you can create and test it. You can select the number of qubits, you can select the number of gate operations, circuit depth and width, etc. In this case, the thing is we are not limited to the coherence or decoherence time. We can do and understand. But later on, you have to look for that also and try to implement within these microseconds. Code programming, as I've said just now, use regular programming codes like CRAQ or Python on the quantum computers to create this quantum circuit and do the simulation. In our open source, we offer 3 types of programming syntaxes. That is Python, Quasm, and Qiskit. And we give the libraries. And we also provide APIs for creating your own custom gates and new algorithms. Am I going fast or I'm okay?
It's okay. It's okay.
Fine, fine. So, okay. Now I am giving you a physical, how our quantum computers appear physically. Now, this is a interchangeable qubit quantum computer. This comes in this shape as a briefcase, suitcase. Open it. We have the samples here. We have the FPGA measurement and control systems, RF systems, temperature control, and these are we need to keep the temperature within 30 degrees that can be set. For that, we have a separate PID control that also uses FPGA, and this is up 1, 2, 3 interchangeable quantum samples. This one is also similar, except it's only 1, 2 qubit, small one, and uses tab kind of arrangement we have where you to execute the quantum going to learn everything, all the programming, learning firmware, courseware are all here. If you look at it, sorry. Yeah. This is a 2 qubit quantum computer which can be connected to external workstation with open software, but we can only transfer the quantum circuit you created through the network, and it can only be executed on the computer. Here you can execute from an external computer. So this is provided with a 23-inch touch PC where all the firmware are. This is a window-based system. Connect to any quantum computer, any computer workstation. It's a 3-qubit quantum computer, ideally useful for classic hybrid quantum computation. Now I have an example of how our
I think sound is not coming.
sound is not coming.
Yeah.
Oh, sorry. I don't know how to share it. I'll send the video separately, sir.
Okay.
You can share it with the participants.
Sure. Thank you.
I can cover. See, the thing is, then I can do one more. Now, this is a sample, quantum sample. Interchangeable quantum sample.
In addition to the video, all the PPTs are also you can please send.
Yeah, I'll try to send. Sure. So this
So
is a
how
sample.
much it will cost to open a quantum lab in the institute? Have you got an idea about the cost involved?
Yes, sir, we have an idea and we are giving a lab. As per the AICT norms, if you go by, including quantum optics, quantum cryptography, quantum sensing to some extent, quantum computation, we can go around about 70 lakhs to 80 lakhs, we can do everything.
Mr. Prasad, after finishing, I think those things we can discuss.
Yeah, correct. No, the video is going on. So,
Mhm.
so this is where we can use DSO or spectrum analyzer to understand the physical frequency response. I'll stop at this and go to the next stage.
Yeah, I think.
So we go next vertical, quantum communication. Now, quantum communication has assumed a lot of importance because now this can be implemented in the form of QKD encryption in our communication and fiber optic communication from place to place or free space. It is being used now, satellite communication or free space or fiber communication. Now, for this, also we need to have a physical system, a learning system at your institution. So for that, we need to have the system which can also give you basic theoretical foundation on this, building a classical channel of sharing information from one to one. If you see cryptography, we call it Alice, Bob, and eavesdropper. Alice being the sender, Bob being the receiver, and eavesdropper is the third one who's trying to do the hacking. Now, first we build a classical channel, send and receive information from Alice to Bob. Do the same thing in a simulated quantum channel, do the same thing. And once you receive it using the quantum keys, we need to have a small information on how these keys are given. Sir?
Yeah.
Okay. Now the thing is, in QKD, what we do for each bit, we add a face, and that face can be, if you want to visually, you want to compare, take a light and then you have a slit in front of the light. If you have a horizontal or vertical or diagonal slit, then the slit can, if you have a horizontal line slit, you can have only that much of light passing through the what we introduce. That is what we call as a face. Now for each bit we add this face, either horizontal, vertical or diagonal, each face for each bit. Now if you add these are the keys we are providing, that is base and the face. Whatever 0 as a base or 1 as a base in binary, for each 0 and 1, different phases are provided, which is the key. Now this key, what you have, you share it with the receiver, Bob. Now Bob, if he uses the same key, is going to receive all the information that you are sending. In between, because of some factor or that, then you will receive only part of the communication sent, even if you use the right keys. That part of it, what you have received, that process is called sifting. Key distribution is what you make and distribute, and sifting is what you receive and compare. Now, this transmission on the receiving part is basics of quantum cryptography. Now, we introduce a third person to understand if there is an hacking or interrupter or eavesdropper. We have another channel, eavesdropping channel, which comes in between. He will try to understand what kind of phase he can do. Say 0 and 1, horizontal, vertical. He'll try to put his own sequence and try to gather information. He'll not be successful, but he may receive some information. Some of them he will, because he's put a wrong keys, he will be in between and then stopping the same thing received by the receiver. So ultimately what we do, the receiver compares the data with the sender, and if he's received less than 30% of what has been sent, then we assume that there is a eavesdropper in between, and we change the whole key and the process. So this is cryptography, and this we learn really physically using we are using in a normal case it is photon and quantum random number generator, etc., etc. In our lab size we use free space, laser source is used, visible laser source, and we are using polarizer to have this phase introduced and phase received. In the thing is how much we can advance, we have done the advancement in our trainer. What we provide motorized polarizers, so we can program the data that we are sending as far as bits and data is concerned, word or sentence, whatever we want to send. For the creation of the phases, keys are through motorized polarizer. You program it and you make the system send it with the keys. And the same polarizer, motorized polarizer, is available at the end user WAP site, and he will receive the thing. Now the eavesdropper is introduced with the two polarizers. So two multipolarizers, so that he can manipulate. So for instance, he doesn't know whether it's 0 or 1. So what he can do, he can split the beam into two, and you can put 0 and 1 in each. 0 and 1 and 1 in another. So like that, he'll try to decode. So for that reason, you'll have multiple two polarizers, eavesdropper, and he'll try to try to hack the data or listen to the data. That's why it's called eavesdropper. This is we are giving with the physical training system. So this is what, if you see, this is Alice, Bob, and we have the eavesdropper. So this is a system with the programmable, easy to learn Python program will be there, and we use Android. So Arduino as a board, as far as the board is concerned, it will be Arduino for learning system. Any questions on communication or computation as of now?
Either, I think,
at the end of it, we can.
message, maybe at the end. I didn't find any queries on the message in the chat box. Please put. I'm telling the.
Yeah. No. Right now, I am not looking at the chat box.
I am looking at it.
Okay. Okay. Now going to quantum sensing. Quantum sensing, we have just explained. In the beginning, I have explained this is because of the quantum, the inherent properties of quantum. We can measure very, very minute changes in certain fields. But the basic fundamental part of it is it uses Zeeman effect, and Zeeman effect is splitting of the electronic nuclear energy. That is level, sub-levels, meaning the two-level system, simple to understand, low level and high level, when excited or exposed to a magnetic field. When export, it splits energy into two. Now, this splitting, multiple splitting or double splitting, can be used to understand. And NV centers are nothing but nitrogen vacancy centers. These are all doped centers, artificially doped, heavily doped in a diamond. In a diamond, the carbon is replaced by nitrogen, and one vacancy is also created. So when the lattice, if you see the lattice, each one will be connected in all four sides. So the lattice, we use this nitrogen and connected to the vacancy, that as the quantum a particle or bit to use for this operation to do the quantum sensing. This NV centers are very sensitive to changes. So these changes could be magnetic fields change, which can be used for earthquake, etc., temperature, minute temperature changes, strain changes, which can be used for structure, huge structures, to understand corrosion part of it is there or not, because corrosion is again magnetic property. These are all practical applications being done. Being a nanoscale, it is, the resolution is nanoscale. So this is again a spin qubit. So fundamental properties of Rabi oscillation all will be there in this. And this also has entanglement part added to it. To if there is an entanglement, multiple NV centers can be used to increase the accuracy part of averaging it, the measurement. The quantum sensing as a lab can be created by a diamond sensor head with optical and electro components in the main control and measurement unit. Which will have all the laser, RF generation, etc., and connected to a data acquisition. These centers can be used for this that optically detected magnetic resonance. This magnetic resonance, according to the field strength, at particular frequency like 2.87 gigahertz, very particular in diamond, you will have the resonance. So that resonance is one factor that we can use. What we do is we apply green light, and the fluorescence that we get, red fluorescence that we get from the diamond is used for the measurement. And with the real quantum sensors, we can use this sensor. We provide this also as a quantum sensing as a lab, as a whole system we provide, and that can be used. But in ACT and NQM, what they have done is they want you to understand at least Zeeman effect. So Zeeman effect apparatus is included as a list of equipment. So that is there, and we also provide the same thing. This is a Zeeman effect. The left one is the Zeeman effect apparatus. To my left, sorry. This is Zeeman effect on the left, and this is a quantum sensing kit. This is the sensor head. So nearer to the head, whatever sample we provide will give results. This is connected to a computer to give you the ODMR, etc., etc. All those things can be understood. It generally will give 8 resonances because it is 4 lattice. 111 is a lattice formation, so 8 resonances will be there. So we can understand there are some advanced techniques also involved, like hyper lines, hyperspectral lines, etc. These are all people who are very, very keen on this particular subject can go deep into it, but we also provide this. Apart from that, as I said, we have now covered the main core subjects. But what about creating a law with the basics and fundamentals of it? So that is required, and the lab can be inclusive of these things. Optics, polarization, diffraction, interferometry. These studies are important. For that, we have these kits: diffraction, polarization. This is a Michelson interferometer. Advanced one is a Mach-Zehnder. The difference being Michelson will have 1 beam inhibitor and Mach-Zehnder will have 2. We also need some training and measurement system. As I said, the basics are also there. So for the basics of electronics, RLC circuits, these are all the circuits which are used in our quantum measurement control circuits, and whatever we create as a total factor, that is measurement factor or control factor, we need these things. RLC, digital circuits, to understand difference between a basic computing and quantum computing. FPGA, particularly because FPGA is a board used. FPGA is embedded system used. Whether it is NMR based quantum computing, the basic lab we provide, we are giving that only because of that reason. In superconducting also, the racks, measurement and control racks, those boards are all FPGA boards. So we do the programming, etc., but fundamental electronic control boards are all FPGA boards. We have the test and measuring system to understand the parameters. Now, vector network analyzer, S parameters the same. S0111 is the parameter of the filters, attenuators, etc. And communication training system is given for transmission and reflection measurements of RF cable. We have included this with respect to what we are giving as a quantum computer or communication we have provided. So all these are connected to some extent what we provide as a learning system for the core learning system. These instruments can also be used there. There is also RF lab with my MIC components, RF component. That's it also you can add. So all these things are available for you to fully satisfy the requirement of what is being given as a guidelines by ACT or NQM. So these are all given for that. If we don't require this, we want to have a center of excellence on only basics and fundamentals or applications of quantum technology. All that we have given earlier, quantum computers, quantum communication, and quantum sensing will suffice. These are all for the lab to create the course, UG minor degree course, where the students are given a brush up on fundamentals.